Alright class, good morning everyone. Let me check that everything is fine here. Morning Mohammed, Mina, Jacqueline, Jordan, Nicole, Sam and Timothy, thank you for being here on time. So I added today's presentation to our in Blackboard. It is under test number 3 lecture material, and also there is two more documents there. One is laws of exponent and logarithmic functions. Those are the ones that we are going to use today. So we are doing lecture 10. We're using lecture 10, so that is the presentation I'm going to be posting here or using for our class. And then I will go back and forth within the 3 documents that we are going to be working today. Okay, any question before we start our class? Yes. Okay. Okay. Announcement. I almost done with the draft of the final project. So you should be receiving my feedbacks by today afternoon. I haven't started with the test. I wanted to have everything done by Sunday, but yesterday I couldn't finish. So expect for today the feedback of your draft. Okay. All right. So let's change this and let's start our class. Before I need to take this. Okay. So last class we worked with compositional functions. Okay, composite functions, and we need to remember from there the definition or the meaning. Let me change this color. Of this operation. Okay. We also need to remember that one-to-one functions have inverse. Okay? And when we apply the composite function operation with inverse functions, what do we get as a result when we use the function and its inverse in a compositional function? What do we get when we do that operation? Okay, so those are questions. That's a question that is going to be important for today. Okay, because now we are going to be working with exponential functions and logarithmic functions. Okay, and these 3 concepts here, okay, are going to be important to understand the relation between the exponential function and the logarithmic functions. Okay, but we are going to start with exponential functions, and the first thing that is important here is that you well know the laws of exponents, and this is one of the documents that I post on Blackboard. So here I put 11 properties or 11 laws of exponent. if I could say that, I could name these 11 properties that way. Okay, I'm not going over this, but this is something important that you need to know, understand, and you need to know how to use it. Okay, if you have particular question about each of these properties, let me know so we can stop and work on those questions. But if not, keep this, because this is a document that you will use as a reference when working with the equation that I'm going to be presenting here today. Okay. All right, so what we want to do is to start, let me double check everything. Yeah, is to start, let's do the definition of what an exponential function is. All right. The main thing here is that here is our function. We need to remember that here x, or x is going to be the input, so here is the argument of the function. And what's going to be important is that the input of the function, now in the function definition, in the equation, the input is on the exponent part of the function. So the x value now will apply as a power to a base, to a value. That value is going to be represented here with the letter A. Okay, so that is our base. Well, we're going to talk about that just in a moment. The most important thing here is that the input of the function, you can find the input of the function as a power in the equation of the function. Okay, so that is the first requirement to have an exponential function, is that the input of the function acts as it is a power, or applied to in the equation of the function as a power to a value. Okay, what that value is, or how we are going to identify that value is going to be, we are going to identify that value as the base of the exponential function. Okay, so A is the base, okay, and C is just a constant. If I can use a different color, okay, it's a factor that is going to be multiplied by the entire expression. Okay, so it's going to be a constant. Let me use parentheses to show you the two parts that we have here in the exponential function notation. Okay, so we have the part where we have the exponent, and that exponent is the input, or the value of the exponent is based on the input of the function. Okay, that exponent, that value, the input applies to a value which we are going to call the base, right? And we could have a constant factor that is being multiplied to that expression. Okay. So using blue for A. So A, we are going to call it the base of the function. Okay, it's going to be constant. It's going to be positive, and this is going to be interesting. Why should it be just positive? Not equal to 1, because if we have A equal to 1, then 1 to whatever power we are going to raise the number 1, at the end we are going to continue having a value of 1, and that will give off a different kind of function, a constant function. Okay, so A is constant, is positive, and not equal to 1. Why should it be just positive? Why not negative? Also, in application, when we start applying exponential function into real world situations, the base is going to be called the ground factor. Okay, but we are not going to cover that part here. Okay, we are going just to focus on the notation of exponential function and its parts. C, as I said, is a constant real number not equal to 0. If C is equal to 0, then again we will have a constant function with just a horizontal line on top of the x-axis. And we have another important property is that we are going to call the initial value. So we are going to have a specific value of this function that we are going to call the initial value. And that is when x is equal to 0. Okay, you will see that the initial value also related to an intercept. Which intercept is related to this one? X or y? Okay. If the value of x is 0, then are we talking about an x-intercept or a y-intercept? Let me know in the chat, or you can just mute yourself. Okay, Jordan, you're asking if x, anyone else, if the value of x is 0, are we talking about an x-intercept or a y-intercept? Okay, so thank you, Alex. Yes, it is a y-intercept. Remember that having an x value of 0, the coordinate, we don't know exactly the y value in this case, but what is going to be guaranteed is that the x value of that coordinate is going to be 0. So we are on top of the y-axis. Okay, so the initial value, okay, is also related to the y-intercept because the x value is equal to 0. We are going to see that just in a moment. Okay, I would like to stop here for a moment, and I would like to go to Desmos because let's explore the meaning of why the base need to be positive and not negative. Okay. All right. So put this here. That's a number. Don't care about that's a number. Don't care. Okay. So I'm going to. I'm not sure how well you see it here, but C. I'm selecting the value for C, just A, just equal to 1. Okay, for the moment. And I have here the value of the base equal to 1. So that doesn't, if a is equal 1, we do not have an exponential function because a needs to be positive, not and different than 1. So let's see what happens if we increase the value of a. So you are seeing the shape of an exponential function. So this is an exponential behavior. Okay, exponential behavior is something that it is very used in, I think, very used in when we speak outside of the math environment. Sometimes you will use the phrase it went up exponentially. That means that it go up, it increased very fast. Yes, Timothy, I'm going back to that just in a moment. Okay, so I want just right now to pay attention. I want you to pay attention of the value of the base. Why the value of the base need to be positive? Why cannot we have a value that is negative for the base? And let's see what happens. Well, let's use Desmos to see what happens if we go and we make a negative. So are you seeing this? Are you seeing how then the curve or the graph, instead of being a curve, it becomes just points. Points that they follow like a shape. There's something like they are tracing a path, but they are not connected. And why is that? Okay. So this is a good exercise to explore why A need to be positive. Why cannot we have A to be negative? So yeah, but I'm not going to go deep here. I'm just going to mention this just as a curious thing because I believe it's interesting. So you can go and play with this function in Desmos, okay? And try to figure out why A cannot be negative, okay? The effect of the constant value, we can see here that if the constant value, remember, is a factor, it's outside the input group, so it has an effect on the y coordinates, so there is a transformation there. So if we increase c greater than 1, we are stretching vertically the graph. If we are between 0 and 1, we are compressing vertically the graph. And if we make this negative, so we have two transformations. We have the stretching or compression, but also we have the reflection over the x-axis. Okay? So yeah. Let's continue. Let me put this here. Let me put this equal to 2, because we are going to get back to this. Okay, so we have seen that A indeed cannot be a negative value. Okay, but why is that? I will let you that to explore. If you have a guess, or you find the reason why A cannot be negative, please share that with me. Okay. So Timothy, you asked for the initial value. The initial value, it is here. Okay. Perfect. Great. Okay. Okay. So we have others properties of the exponential function. Okay. First, we are seeing that there is no restriction. Let's focus again on the input. There's no restriction. The input is not on the denominator. It's not in a radical expression with an even index. So there is no restriction here. So that means that all real numbers are the domain. So we can put any value, any real number there, and we are going to get a value. Now, for the range, this seems kind of weird. Well, there's no restriction in the domain, so maybe we should expect to be to get a range with all the real numbers, but that's not the case with exponential function. The range starts from 0. We are not going to include 0, and it goes to the infinity, to positive infinity. Okay, and this has an effect on that we are going to take into consideration. That is going to be important. Because this is related to the horizontal asymptote. And what is an asymptote? An asymptote is a line in the plane that will determine two regions of the plane based on the function that we are working with. Okay, and usually horizontal asymptotes mark a region where we are not going to have any kind of value or curve for that function. Okay, so let's go back to this and let's explore that part. Okay, so here, if I zoom out, I'm going to continue seeing that the curve never goes down, never goes below the x-axis. Okay? So let me create a representation of the asymptote. The asymptote is not part of the curve of the function. But usually it's something that we put on the plane to as a representation to know that there is an asymptote. So this is equal to 0. Let me change the style. Okay, so the dotted line is representing the asymptote. The asymptote, if we zoom in, zooming out, it seems that like the graph is and the asymptote overlap each other, that they are in the same place. That is not true. The asymptote here is like a wall. The asymptote is marking two regions in the plane. The region where we are going to have the curve of the function, where we are going to get value for the function, and the region that there's no value for the function, that there's no curve of the function. There's nothing below there. So you see that this graph never will go below the x-axis. So that is why the asymptote is important. Timothy, go ahead. Say one more time. Yeah, it will not get to 0. So it seems, if we go to the left, it seems that, wow, it's getting closer and closer. And now we are seeing it, and we can say, no, the curve and the asymptote are in the same place. Well, let's zoom in to see if that's true. Every time our curve will get closer and closer and closer to the asymptotes, we never go, it will never touch it. It will never cross it. Okay? So the asymptotes also are important because they are going to determine the shape of the graph. Because the asymptote, if we know the asymptote, we will, for exponential function, we will know that the curve will try to get to the asymptote every time. So it will, the asymptote is, you can think of it, is like a magnet for the curve of the graph. But the graph would never reach it. Okay? So we have two regions here that we are seeing two regions. Let me put this here. Okay? We have two regions. Above the x-axis, we have value for the function. We have a curve in the plane. Below the x-axis, there's nothing. And the asymptote is marking those two different regions. This is also have an algebraic explanation. And I'm going to ask you, let me set up this here. My question for you is, can you think of a value for x that we plug into an exponential function and we receive a negative value? Let me make this more clearly. Let's suppose that c is equal to 1, right? And then the base is 2. So what we have is, focus on this equation. Okay. So here is one. And what you're saying is that the function value needs to be greater than 1. So that is true for only this part. When the value of x is greater than 0. Okay? Let's go to the law of exponent. The law of exponent says that if we raise any value to the power of 0, the result is, so let's see, x equals 0, we are going to get f of 0, which is the initial value, okay? 2 to the power of 0 is just 1, and that is that point, the y-intercept 0, 1. but see that the domain of the exponential function is all the real numbers. So that means that we can include negative value for the input. Okay, not negative value for the base, but yes, we can include negative value for the input. So let's see if we use, let me go around here. If x now is equal to -1, so we have f of -1, this is equal to 2 raised to the power -1, going back to the law of exponent, the effect of this negative in the exponent creates or gives off the reciprocal of the base, okay? And we raise all that to the power of 1, but 1 and the power of 1 just stay the same, the result is the same. So that point now is, this point here, the coordinate is -1, and 1.5, positive 1.5. Okay, so Timothy, I understood what you said, but the thing is that you only thought of no x input greater than 1. We can include negative values as the input of the exponential function. Okay. X is going to be, the domain of the function is all real numbers. So x is going to be from negative infinity to positive infinity. It could be anything there. No. I think you are getting it. Because my initial question is, can you think of any x value that we return from of a negative value of this function? So okay, Mohammed, you said you put 2 there. What do you mean by that 2? Timothy, you are thinking just going to the right side. Thinking, you need to think that same concept, that same thought, apply that same thought to values of x that goes to the infinity. And you will see that the graph will continue giving us, or the function will continue giving us positive values that get closer and closer to 0. Okay? The range of the exponential function goes from 0 to positive infinity. Okay? We can get very, very close to 0. It never will reach 0. Okay? But to go back, and so now to go back to the original question, is there any x value that we can plug into this function and we receive a negative value? The answer is no. Okay? There is no way we can get a negative value from this equation. And that is the meaning of the asymptote in the horizontal asymptote on top of the x-axis. Because there is no possible way, algebraically speaking, to get a negative value out of 2 to the raised to the power of x. And that is the reason of the 2 regions where we are going to have the curve of the function and where we are not going to have anything. When we are going to receive values for the function, all of them are going to be positive in this equation and no negative values. And we are going to, okay, when we start looking for on the examples, I hope that you are going to start graphing this a little bit better. Okay, remember that we are still working with, we are starting with the properties of the exponential function. When we start looking at and working with example, you will have a more concrete representation of this meaning. Okay, so there is no x-intercept. Why there is no x-intercept? Because we have an asymptote there on the x-axis. So the graph will never touch the x-axis. algebraically speaking, what is the meaning of that? There is no value of x. There is no value that we can plug into the function and we receive 0 as a value. Remember that if we go to the left side, if we go and use a smaller x value, so that means that we go to the infinite, to a negative infinity, okay, the graph will tend to go lower and lower, getting closer to the x-axis, but there is an asymptote there, so the graph will never reach the x-axis, so there is no x-intercepts in this case. Okay, there is no x-intercept unless there's transformation, but we are going to talk about that in just in a moment. There is no x-intercept, but yes, we are going to have a y-intercept. Okay, we are going to have a y-intercept, and that y-intercept is the initial value, because when x is equal to 0, okay, we can plug in 0 into the function and we can use 0 as a power. That will turn the base, the value of the base, equal to 1. If the value of c, of the constant, is 1, then the y-intercept is 0, 1. If the value of c is different than 1, then the y-intercept is at 0, c. But let's see that in Desmos as well. Okay, let's put c equal to 4.9, and we go here, and there is the x-axis, the y-intercept. The y-intercept is at 4.9. Okay. So we have a horizontal asymptote. The horizontal asymptote is at the x-axis, or we can say that it's the x-axis because it's on top of there. 1 on 1, the exponential function that we are seeing right now, because we are not talking about yet about values for the base, different values for the base, and this could be base being less than 0, less than 1, or greater than 1. But if we consider a to be greater than 1, so we have an increasing behavior, and it is a one-to-one function. And this is going to be important, one-to-one function, just in a moment, because we need to remember that if it's a one-to-one function, then that means that the exponential function has an inverse function. Okay, but what is that inverse function? Let's see. We will see later who is the inverse function of the exponential function. Okay, so let's see that again on Desmos. So a being 2, c being 4.9, there we have an increase in behavior. If we move to the right side, the curve goes up. And we have 3 key points for the exponential function. And look at the shape or the format of those points. Remember, the first that we are going to use the easiest value as inputs. The easiest value are, the first one is 0, the other one that is easy to use is 1, and the other one is -1. So we are going to use -1, 0, and 1 as the x value for the key points, okay? And we need to, I'm using c now equal to 1, so I have a raised to the power of x. So when x is -1, using the law of exponent, that brings a into the denominator, so we got the reciprocal. That's what we have here. A raised to the power of 0 is just 1, and a to the power of 1 is just a. So those are the 3 key points. Okay, so it is easy to get the key points, you're thinking of this format. With -1, we go and use the reciprocal of the base. With 0, it's just 1. With 1, okay, x equals 1, we got just the value of a. With x equals 0, we got just 1 if z is equal 1. If not, then it would be the value of z. And also, this is the initial value. That is the initial value. So the initial value is part of the key points. And the initial value is also the y-intercept. Okay? So this is a summary with an example. That is the example that we've been working on Desmos with base equal 2, c is equal 1. So the domain is all real numbers. The range goes from 0 to positive infinity. There is no x-intercept. The y-intercept is at 0, c. The value of c here is 1. So here is the y-intercept 0, 1 because the value of c is 1. Okay, we have a horizontal asymptote. Horizontal asymptote is here on top of the x-axis. Remember that it marks the two regions. It is increasing. We are seeing the behavior that is as we move to the right side, the curve goes up, and also this arrow here is pointing up as it moves to the right side. It is a one-to-one function. This is going to be important. Why? Because there is an inverse function then, and we are going to learn what is the inverse function of the exponential function. And the key points, see the format, -1, 1 over a, 0, 1, and 1, a. Let's identify those three key points here in our graph here. So with -1, x being -1, the value of the base is 2, so it will be 1 over 2. So that is this point here. The y-intercept, the initial value, when x is equal 0, the value of the function is just 1. So that is the second key point, and then the last and third key point is when we use 1 as the input, then the y value or the value of the function is going just to be the base if z is equal to 1, which is in this case, yes, z is equal to 1. Any questions so far? Okay, so we need to remember of the transformations. Okay, remember the effect of the transformation. See that horizontal shift is being in the input group, vertical shift is outside the input group. Okay, so can you tell me the description of the transformation here? Let's start with this one. Can you describe what is the transformation? Can you describe the transformation here? It's a vertical shift, but are we going up or are we going down? Nicole, I didn't hear you. Can you repeat? Up. We go up by 1 unit. Okay, when we subtract, we go down by 1 unit, because here we are adding by 1 or we're subtracting by 1. So this is going up 1 unit. This is going down 1 unit. Okay, this kind of transformation, vertical shift, are important to the horizontal asymptote. Why? Because now the graph is moving moving vertically, and that means that the horizontal asymptote also is going to move. Let's go to this, see it. Okay, so let me do here, let me use K. 0 x plus k. Okay, so what I'm going to do is to in our exponential equation function on top, I'm going to add by k. Okay, so I adding to the equation, so there is a vertical transformation, there is a vertical shift here depending on the value of k. If k is positive, we go up. If k is negative, then we are subtracting, we go down. And let's see the effect not only on the graph but also on the asymptote. Let's put k, let's increase the value of k. Let's put k equal to something that is positive. So see how the asymptote moves as well the graph. Okay, so vertical shifts are important because they move the graph, but they also move the asymptote. And the effect of that, we have two things. The asymptote changes, okay, the location of the asymptote changes. But now, if the asymptote is if the value of k, if we move down, if we shift down the exponential of graph, now we are going to get x-intercepts. Okay, that's important. Normally, if we are not, is there no transformation, exponential function do not have x-intercepts unless we move down. We do a transformation where we move down the function. So now we are getting x-intercept. Okay, and you can see that our vertical asymptote moved as well with the value of k. Okay, so keep that in mind, because unless there is no transformation, vertical asymptote will not have x-intercept, it will not have zeros. But in case we move down the graph, okay, in this case we subtract to the value of the function, we are doing a transformation, a vertical shift that goes down. Okay, remember the horizontal shift, if we are adding, it moves to the left. If we are subtracting, it moves to the right. We have reflections. When the c value is negative, we have a reflection over the x-axis. Okay, and we saw that already. But now I want to focus on the other reflection, the horizontal reflection. Okay, we are going to get back here. Okay, but I want you to think of this and what is going to be the effect of that negative in front of x. Okay, we know that if we have multiplied the x variable by a negative, we would have a horizontal reflection, a reflection over the y-axis. Okay, but this has a deeper meaning when we are working with exponential functions. We are going to see that just in a moment. Okay, so now we have sample number 2, where the value of a, the base value, is 1/2, is less than 1. Also, it's greater than 0, but now it's less than 1. So what we are seeing here is that now the shape of the graph, or maybe the direction of the graph, it changes, right? Or the behavior of the graph, definitely it changed, because originally when a is greater than 1, we have an increasing 1-to-1 function. But here now we are seeing a decreasing 1-to-1 function. Okay? Before we answer everything here, let's continue exploring the value of a being less than 0. Okay? In example number 1, the value of a was 2, greater than 0. Okay? So on the right side we have f of x equals 2 to the power of x. On the left side, we have f of x equal to 1 over 2 to the power of x. By looking at the graph, can you identify the transformation that happened here? Do we have any kind of transformation between these two graphs? Or is there any transformation that you could think of that could describe these two graphs? Inverse? Inverse is not a category of transformation. Jordan? Yes, reflection. So what we are seeing is a reflection. We are seeing a horizontal reflection, a reflection over the y-axis. Okay? But we are not seeing a negative in front of the input. For example, let's focus here. So if these two graphs, if we can describe these two graphs by a horizontal reflection, a reflection over the y-axis, why are we not seeing a negative in front of the x variables? Because we know that if we have a negative in front of the x variable, it means that there is a horizontal reflection. But we are seeing a horizontal reflection in this graph without that negative from the x. And that will take us back to the law of exponent. Because yes, we have a reflection. And yes, there is a negative in from the x variable. Okay? Remember that if there is a negative in the exponent, that the effect of the negative is that it takes the base and it gives us back the reciprocal. Okay? So we can think of this function as 2 raised to the power of negative x, and there is the reflection over the y-axis. Okay? The effect of this negative turns these two into 1/2. It's reciprocal. Okay? So now we are ready to answer all this. The domain, is there any restriction on the domain of this function here? What is the domain? Negative infinity to? Correct. Okay? Remember, exponential function do not have any restriction on the domain. So, pretty sure you always can answer the domain for all exponential function. Well, the domain for all exponential function is all the real. So you are going to be sure always on that. Range. What is the range? Just by looking at the graph. Remember that this is an asymptote. 0 to infinity, correct? Intercepts. Do we have any x-intercepts? No x-intercept. Do we have any y-intercept? What is the coordinate of the y-intercept? 0, 1. Yeah, y-intercept is 0, 1. Oh, so that means that our c value is 1. Okay, the initial value here is 0, 1. C, the value of c, the constant, is 1. Okay. Horizontal asymptote. So how are we going to identify horizontal asymptote? By this equation. Y equals to 0. If you just put 0, that's incorrect. the way you identify the asymptotes is by an equation. The equation of this asymptote, because it's a horizontal line, you need to put y equals to that value. Since there is no vertical shift, y equal to 0. In the cases where we have vertical shift, y is going to be equal to the unit that we move up or down the graph. The behavior now is decreasing, and this is important because the behavior of the exponential function changes. If a is greater than 1, we have an exponential growing behavior, an exponential increasing behavior. If a is between 0 and 1, it has an exponential decreasing behavior, and that's important for future exercises that we might be working with when we apply exponential function into real life situations. Okay? If you are interested in biology or chemistry or biological sciences or science in general, you will find that exponential functions are used very commonly in living organism studies. Let's say yes that way. Population. Thank you, Timothy. It is very commonly used in population. A lot of equations that describe how population grows or how population decay are based on exponential functions. Okay. And the key points, you need to remember always that the key points are going to have the following format: -1, 0, and 1 for the x values, and then for -1 is going to be 1 over a. When 0, that is the initial value, because c is just 1, so it's going to be 1, and when x is equal to 0, the exact a value. But a, the value of a here is 1/2, right? Is 1/2. So a is 1/2. So we have 1 over 1/2 that gives us back 2. Remember that we are dividing two fractions. So we use the reciprocal of the second one, and we multiply the first one, the one that is on the numerator. 1 is a whole number, but also a fraction, 1 over 1, times 2, we got back the value of 2. Careful, a lot of you might confuse this negative and we put a negative in front of 2. That is a very common mistake. That negative, remember that we are talking about in the exponent. That negative is in the exponent. So what it's going to do is to give us back the reciprocal. 0, 1, and then 1 over 1 will give us the value of a, which is just 1/2. Okay, so these are the key points. So we have -1, 2, 0, and 1, and then 1 and 1/2. Okay, and we can identify those points here. -1 and 2, the y-intercept, the initial value, and 1 over 1, 1 over 2. Those are the tricky points. Okay. Any questions so far? All right. So this is you will find in the next slide that is just what I just talked about, the properties of the exponential function when the value of the base is between 0 and 1. Okay, so now let's do this exercise where we are going to graph the exponential function. Okay, first thing that we are going to do is to identify the parts of the exponential function. Let's start with the domain. Domain, no restriction, from -infinity to infinity. Okay, range. Originally, the range goes from 0 to positive infinity. So I'm gonna use a different color to put the domain of an exponential function from 0 to 2. But our exercise is not just the general exponential function. There is a transformation there. Can you tell me the effect of this -2 there? What is the transformation here? Down 2. So down 2, did I write that part? Let me double check. Yeah. Okay, we went down 2 units, right? So the effect of this is not only on the graph, not only on the asymptote, it's also on the range. So now the range is from -2 to positive infinity. Okay? Careful with that. What else? Horizontal asymptote. HA, horizontal asymptote. Originally, the horizontal asymptote is y equals 0, right? Well, there's a transformation. So our horizontal asymptote now is y equals -2. See how I'm writing and identifying the asymptote? Y equals is an equation. Identify the base. Let's identify the base, the value of the base. Can you tell me the value of the base and the value of the constant factor? Can you identify the value of the base? The constant factor. We are going to focus only on this part because the part that composes the exponential function is where we have the input as an exponent. Mohammed, that's correct. The base is 3. Okay, how do we identify the base? It's directly to which value the power of x applies to. Okay, x applies directly to 3. Okay, so the base is 3. Now, are we seeing any other number in front of 3 that is being multiplied by that? This is tricky here. Sometimes this is going to confuse you, but you need to always think of the order operation, because the order operation will help you to read the equation. The power applies first, so if there is no parentheses covering other numbers, so the base is directly the number that is attached to that exponent. Okay, so that is how we identify the base. The base is 3, but there's no other numbers there, so that means that the c value, the value of c is 1. So base is 3 and c is 1. Careful with that, Timothy. Yes, 3 is prime, but again, we are going to see an example where c is not 1, and so we can identify correctly base and the constant value. Okay. All right. So the next thing is to graph. Whenever we are going to graph an exponential function and there's an asymptote, what we are going to do, we are going to start with the asymptote. Okay, we want to tell the reader where the asymptote is. And I'm not going to be precise here, but I know that the asymptote goes 2 units down, so my asymptote is this dotted line, and I'm just going to identify I'm going to label that the asymptote as y equal to -2, okay? That way I can see the representation of the asymptote. Again, I'm not being precise here. I just want to represent the graph. And I need to remember that they are key points. The format of the key points, let me put it here. The key points are -1, or 1 over a, 0, 1, and 1, comma, a. I need to remember that it's a transformation, that my y values, the y coordinate goes down 2 units, okay? So the value of a is 3, right? The value of a is 3. So what I'm going to write here, I'm going to use a different color. This color is with no transformation, no transformations, okay? Because our exercise has a transformation that goes down 2 units. But first I want to see the format of the key points, and then I want to apply the transformations. So it would be 1, -1 over 1/3. It would be 0, 1. This doesn't change yet with the value of a. And then it will be 1 and 3. Okay? Again, these coordinates are without transformation. But then we need to apply the transformation. And that transformation is that we have f of x equal 3x minus 2. So that means that all my y coordinates will go down 2 units. So 2 minus 1/3 minus 2, that is going to give a negative value. Mohammed, those points, sorry, I missed your question. Okay, I'm getting those points, this one that are here, directly from the properties of the exponential function. Let me go back a few slides. Okay, let's go. Let me start over. Okay, the key points. Okay, and slide number 5, I believe. There are properties of exponential function, and the key points of the format of the key point are here. Those are the 3 points. Okay, inverse operation, Timothy. Careful using the inverse word here. Remember that now the word inverse has a meaning. Inverse operation, I wouldn't use that. Not in this context. And you will know why you don't want to use inverse so loosely in this topic. Okay, so I think this is, I don't know, 5 or 3? You will correct me if I'm wrong. 0, 1 minus 2, -1, then 3 minus 2 is 2, okay? So 1/3, 6 over 3. So these are the key points of that particular exercise, of that particular function. The function that is given is 3x minus 2. Those are the key points. So you know what to do. You go here. I'm not going to be precise. I'm going to put it, I think around here, I think around here, and I think around here. I already know the shape. That's the shape. And then I'm going to label my points. Okay? Important that you label your points. We are not going to be precise here. Okay, what we need to do is just to label our points, and that is the graph. Questions? Okay. So there are more exercises there, but I'm going to stop on this one. I'm not going to do the graph of this, but let's practice something that is important. Let's identify the base, and let's identify C. So tell me why the third point becomes 0 of 1. Mohammed, you're talking about the key points. Okay, are you talking about the specific example that we were working, or the properties? Yeah, I made a mistake. Thank you, Mohammed. Yeah. Got it. Thank you, Mohammed. Is 1, comma 2. 1, comma 2. And here again, 1, comma 2. Okay, let me double check that everything is here, right? Okay. Again, thank you for picking up that mistake I made. Okay, identify A, identify C. Tell me A and C. Okay, Timothy, I like the way you are seeing things, but you are complicating yourself. Okay, base is just 1/3. Here, what is important? This is when you are seeing this. When there are use of parentheses. When you are seeing the parentheses, the use of parentheses here will help you to identify and to differentiate between 4 and between the value of C and the value of A. When we have parentheses and on top of those parentheses we have the exponent, that is pointing out, oh, that is the value of the base. The base is 1/3. And then that 4 that is outside the parentheses is the value of C, is the constant value. Okay? Again, Timothy, I like what you're saying. Okay, I like that you're like looking around the equation that you have here, but I don't want you to complicate yourself. Okay? That's it. We are seeing a parenthesis, and that parenthesis contains an exponent. That's the base. Okay? Anything else is going to be part of the value of C. Now, let's identify. Let's identify. Let me write different examples here. 2.1. Let's identify the value of C and the value of A without using parentheses. This is very confusing. I'm not going to write this way, but sometimes you will find things like this. Okay? Now we need to be careful. Obviously, I made a tiny space here to differentiate these 5 and 2 with the number 52. Okay, so this is not 52. What we are seeing here is 5 and times 2 raised to the power of x. Now, can you identify the value of A and can you identify the value of C here? C is 5, correct? And A is 2. That's perfect, correct. Okay, I'm not going to write here like this in the assessments, but you can find that this expression, this is for me is bad expression because it's confusing, but how can you identify the value of A and C here? Follow the order operations. What goes first? The power, right? So the power is on top of 2, not on top of 5. Okay? Well, so the power is telling us the value of the base, which is 2. And this 5 here is not related to the exponent. So that 5 is then the value of C. Let's see another example. So you can tell me the value of C and the value of A. This is acting weird today. 2.2. F of x equals 5 to raised to the power of x. Can you tell me now the value of C and A? C is 0. If you Mohammed is C is 0, then the entire equation is the entire function is 0, and then A if it's 2. That's correct. If you are not seeing C, that means that it is a factor, which is the value of that factor is 1. Remember that when we are working with multiplication and we have 1 as a factor, we tend to omit writing the number 1, so C is just 1. Okay. Another way that you can find is a little bit more explicit, like this one. 5, and we use the dot, and there's a direct separation there, so that dot is multiplication, so that way we know that A is 2 and C is 5. Yeah, we don't. Also, you can also find times using x or cross times 2 raised to the power of x. Okay. Again, yeah, we sometimes math writing is if we do not know the context, we wouldn't know if we're talking about 52 2. So for at least you can expect from me from the assessment that I'm going to use a parenthesis, or I'm going to use a very implicit mark telling you this is a factor, these two factors are separated. Usually I will use parentheses. Okay, and there's another exercise there. That's another exercise. Take 5 minutes. Try to do this one. Try to identify domain, range, horizontal asymptote, identify the base. Keep in mind that there is transformation here. Also, I would like to see if you can identify the transformation as well. Let me see how many do we have. Lab of x, functions. Yeah, just take 5 minutes. It doesn't matter if you cannot complete it. I just want you to start practicing and to create questions. I'm going to turn off my webcam, mute myself, and I'm going to give you 5 minutes to work on this one. Any question, please post it on the chat, or just unmute yourself. Okay, any questions? Timothy, see infinity to infinity, range is 1 to infinity, perfect. Horizontal asymptote is 1, y equal 1, perfect. Jordan? If you can send me a direct message to the chat just to make sure that you are getting it correct. Okay, but I'm going to move now. I'm going to move to the next part because I want to cover. I want to cover with the function equations and how to solve it. Okay, so now this is a very important property that we are going to use because our goal let's say that the main objective of learning about exponential functions is to know how to solve exponential equations. Okay, and this is a property that we are going to use, and let me explain this property for you. Okay, so on the left side, sorry, we are seeing an exponential equation. How do we know that it is an exponential equation? Well, the first thing is that we have the equal sign, and then that we have the variables x and y in the exponent. So once we have a variable there in the exponent, we are working with an exponential what's the word? Exponential concept. Let's see exponential concept because we could have other components in the equation, but as of right now, this is an exponential equation because our variables are in the exponents. So how are we going to work with those exponents? Because we know if we are working, for example, the following equation, we need to solve for x. Well, we subtract both sides and we solve for x. If we have a multiplication, so we divide both sides, right? We use the opposite operation of what we have there, of the operation that are binding the variable x in this case with the other concept or the other part of the equation. Okay, but I believe we have been working only with adding, subtraction, multiplication, division. We have been working with the exponential parts of the equation as operations of the equations. Okay, on how to solve it, how to work with in the exponents. Okay, so this first property is one of those that we are going to use to solve exponential equations. Okay, so what does this say? It says that if we are in an equation where both sides are in exponential form and the bases are the same, then we can conclude that the exponents are also the same. For example, let's say that we have 3 raised to the power of x equals 3 to the power of y. We do not know the value of y nor the value of x, but this expression would tell us that, well, both x and y need to be equals. Okay, let me change y for 2. If I have 3 raised to the power of x is equal to 3 to the power of 2, then we conclude that x is equal to. Okay? So yeah. So this is the type of exercise that we are going to do right now. We are going to solve for x, but x is on the exponent. Okay, so that is the first exercise that we have there. Okay, and it might throw you off. Because you are seeing maybe something new, maybe something that you're seeing for the first time. But this is very easy. This is very easy because you have worked with this type of equation before. The only thing that is different is that our x value, the variable, is on the exponent. How we reach the exponent? We are going to use the following property. Okay. what is important from this property is that we need to have the same base. Okay, so I have here, I'm writing down our exercise. And step number 1 is to determine, do we have the same base? And that's a question. Do we have the same base? What do you think, class? Do we have the same base? Let's focus for a moment on this expression. We have the same base, okay? And we are going to see why. Okay, the exponent part, the exponent. All this is the exponent, all right? So it means that the base right now, the base of that particular expression is 4, right? But 4 is also a power of 2. 2 raised to the power of 2 is equal to 4. Okay? Let's hold that part there and let's focus now on a to the power of x. The exponent is just x. That means that the base here, as we are seeing right now, is 8, right? But 8 is a power of 2. 2 to the power of 3 is 8. So let me go and change. So what I'm going to do is to replace 4 with the expression 2 to the power of 2. And to replace 8 with the expression of 2 to the power of 3. Okay? So let's do that. I'm going to use parentheses so you can see the changes. And I'm going to use a different color. What color is nice to use here? Let me use purple. Okay. So let me copy and paste this. Let me open a new page because we need more space. Let me rewrite all this. So we start with 4 raised to the power of 2 minus 1 equals a to the x, and then we identify that 2, 4, and 8, they can be rewritten as power of 2 because they are power of 2. Okay. Here, now, we're almost there because what we want to do is to use the property a raised to the power of x equal a to the power of y, then the two exponents are the same. Okay, so here what I'm going to do is to apply the law of exponents. Okay, again, if you have questions about the law of exponent, first you have a document in Blackboard you can download with 11 properties of the exponents, and if you have questions how to apply them, just be precise and then tell me your question. I can help you with that. So right now we are going to use this property number 2, where we are seeing parentheses. That parentheses are enclosing x raised to the power of m. On top of that parenthesis we have n, another exponent. That exponent that goes directly to the parentheses. We can simplify that by just multiplying both exponents, and that's what we are going to do here. Let me take a screenshot of that. Okay. So using this property, look what we are going to do. So what I just did is I took this exponent and the exponent. Now they are being multiplied together, so they become just one exponent, one big exponent. I took this exponent, and they just become one big exponent by just putting them together in a multiplication. So now we can use the property that it is here. So we have the same base, and that means that then my exponent needs to be the same. So 2x minus 1 equals the other exponent, 3x. So basically what we did is to cancel the bases. Yes, and we canceled the bases. And when we started working with the inverse function of the exponential function, you will see how is that we are able to cancel and how this property becomes very handy. Okay, so we have the same base, we can cancel the bases, and we can use this property, and now what we are working with is just a linear equation, and you know how to do this. Okay, so basically we are doing the same. The only thing that is that we have a step back, which is an exponential function, and what we need to do is to first get rid of the exponential form. Once we get rid of the exponential form, we are going back to the equation that we have been working before, exponential equation, or maybe a quadratic equation. Yes, we could have. We are going to just be working with linear equations after the exponential part. So see how I went through the steps. Again, these are the steps that I want to see in the assessment. This is how you go and tell me how you reach to your conclusion. And to mark here the number of steps. So step number 1 is to find the same base. Okay, so once we got to here, then we are going to do a step number 2. In step number 2, what I did is just to combine the exponent. So then in step number 3, I can use this property where I cancel the bases and now focus on the exponents. Questions? So x equal to. Okay. Do we have same base here. Yes, we have same base. Okay, 5 is going to be that base, and we need to know how to get to 1 over 5 and 225. So 5 to raised to the power of 2 is 25, so we are good there, right? And then 5 raised to the power of -1 is 1 over 5, okay? So how are we going to transform this or change this? 5 raised to the power of -1, x equals 5 raised to the power of 2, all this over x minus 4. Then we combine the powers, so we got 5 raised to the power of -x equal 5, 2, careful, we have two terms in the exponent, 2 times x minus 4. We cancel the bases, and x minus x equal 2 times x minus 4. This is the linear equation. You solve it for x, and you got the value for that we are looking for. Okay. Again, I'm focusing only on the exponential part. You already know how to do this. It doesn't matter if the value of the base is unknown. Here we have the same base, so x equals to x plus 1. Very easy. We didn't need to do anything else because we already got the same base. So we focus on the exponents. Do you have more exercises here? Okay. Let's focus on this number 3. Number 3. So we need to solve for x. So what we got here is 2 to the negative x, and 16 is 2 raised to the power of 4. So negative x equal 4. And then x equal negative 4. We multiply both sides by negative 1. Okay? This is not the final answer. Remember that x needs to be isolated. So we have a second exercise that will give you 5 points extra on test number 3. Again, you will work with the exercise, you will prepare your PDF document, you will send your work via email with a subject exercise number 2 for 5 points extra on the test. To get this 5 points, you need to get everything right, all the steps and the conclusion. There is no partial points, it's 0 or nothing, okay? And you have the exercise on Blackboard, because you can download this. You can download this presentation. Okay. So now we are going to talk about logarithmic functions. Okay. I'm not going to go further in logarithmic functions. We are going to continue on Wednesday to go deeper on logarithmic functions, but I'm going just to put it here because you need to get ready for the next lecture, where we are going to be working with logarithmic functions. We are going to be working with logarithmic equations, and we are going to be working with both at the same time, exponential and logarithmic functions. Timothy, I haven't graded the last exercise for 5 points extra, so you will know. When I grade your ones, I'm going to reply to that email, and I will tell you if you earned the 5 points extra or not. All right, so let's focus on the way we write logarithmic functions, and then let's see why they are here and what is the relation with the exponential functions. So logarithmic functions, so we are going to use the word the letter log to represent the logarithmic function. See? Okay. Always you are going to get to put as a subscript here, this is going to be the base of the logarithmic function, and the input, or what is going to be evaluated by the logarithmic function, is going to be the argument. Okay, so to have a logarithmic function, we need to have the argument of the function as being part of the argument of the logarithmic function. Yes, we could have no, yeah, to have a logarithmic function, the argument of the function need to be in the argument of the logarithmic function. Other than that, it would be just a number. Logarithmic functions are used to represent other kind of numbers as well, other kind of values. Okay, so if the logarithmic function and the argument is just a value, is a fixed value, then the logarithmic function was giving us is just a value. We are going to talk more about that when we work with exponential logarithmic functions, so you will understand that part better. What's important here is that to know that we have the base and we have the argument. The base need to be constant, positive, not equal to 1. So very similar to something that we just learned, right? And the logarithmic function is the inverse function of the exponential. Okay, so this is the part where we are going to focus more on this 10 minutes that there are left, and that is the reason why you have a second document here. Yeah, log. Asymptote, yes, it has a vertical asymptote. There is a relationship there of inverse, because let's go back to inverse. If f is 1 to 1, right? 1 to 1, so there is an inverse function, okay? And they are inverse to each other. And what is the meaning of inverse? In terms of coordinates, well, the function will give us x comma y, but the inverse is going to give us y comma x, okay? And that has a relation with, if we have a horizontal asymptote, then the inverse we have will be a vertical asymptote, okay? And that is what you are seeing there, Timothy. If you are working with in Desmos, you basically are seeing how it turns. Okay, so what I want you to do is to get used to the logarithmic function. We are going to get deeper next lecture with logarithmic functions, but the first thing that you want to do is to practice how the powers of these numbers, okay, or how to get the powers. So how we got the powers? Let's focus on the initial value, 2 raised to the power of 0. 2 raised to the power of 0 by the law of exponent, that is just 1. 2 raised to the power of 1, that is just 2. 2 raised to the power of 2 is 4. 2 raised to the power of 3, 8, 16, and so on, okay? But if we go back, and now we are using negative value for the exponent, so 2 to the raised to the power of negative 1 is the reciprocal, 1/2. Then we have 2 raised to the power of negative 2. So what we can do is first apply the negative, 1/2 raised to the power of 2, and 1/2 raised to the power of 2 is 1/4, and so on, okay? 1/8. So you now need to practice this because you need to get used to start seeing values as powers of something. So 4 is a power of 2, 9 is a power of 3, 16 is a power of 4, 25 is a power of 5, okay? Because we are going to be working with exponential and logarithmic functions. So you need to get used to look at the values and identify if they are power of another value. To understand the concept of logarithmic functions and to understand that they are the inverse function of exponential function, we are going to do this exercise. 2 raised to the power of 2, what is that value? Did I say 2? 3 raised to the power of 2. Let's do this part. Let me open a new page. Okay, let's focus on 3. Let me correct myself. 3 raised to the power of 2. What is the result? 3 squared. What is the result? Is 9. what we're seeing here is the exponential expression, right? Of 3 raised to the power of 2 equals 9. Let's see the logarithmic expression of log base 2. So if I put here log base 2 of 9, the result is going to be 3. Okay, remember they are inverse to each other. Okay, and I want you to focus on these numbers, and let me change the colors. If you follow the number and also the colors, okay, this with the colors is how they relate to each other. Okay, so log base a, the value of a in this example is 2, okay, and x in this is the argument, but in this example is 9. X is equal to 9, okay. So the logarithmic function, they answer a question. What question is that? Let me move everything down a little bit, if I can. Okay. The question is here. What number is raised? Yeah, I did raised to the power of the base. The base here is 2, okay? What number is raised to the power of 2 let me see, what number is raised to the power of 2 and give us the argument which is 9. Let me double check if this question answer makes sense. To a power what number is raised to the power of 2 and give us the argument 9. Does that make sense? Maybe I need to yeah, I think so. Yeah. What number is raised to the power of the base? The power of the base is 2. Okay. Oh, when the power of the base, I'm referring to the value. What power is raised to the power of 2 to the power of? Let me change this. What number is raised to the power of 2, so the base, and give us 9, the argument. Okay, so the question here is to look for one number I can use raised to the power of 2 and I got 9 back. Okay, so it becomes an equation. What number to I raised to the power of 2, I got 9. And you might think of this that, well, if I apply the square root on both sides, I'm going to get plus and minus 3. And that's correct, okay? Careful when we are working with logarithmic functions, okay, there's a restriction, but we are not going to talk about the restriction yet. I just want you to think of the question, okay? I just want you to think of the question. This is going to be important, okay? The answer of that question is 3, just positive 3, okay? And how do we know that it's positive 3? Well, if we go and look at the inverse, 3 raised to the power of 2 gives us 9. So how are we going to fill the blanks? Log base A represents the power to which A, oh, let me see. Yes, I know what it is wrong. Okay, I mix up the base and the result. Okay. So I'm gonna leave it there because I don't want to confuse you. And then when we start on Wednesday, we are going to start in this question. I'm going to rephrase the question correct when we start on Wednesday, and then we are going to explore more on the logarithmic functions. What I want you to do on lecture number 10 is to focus on the exercises to solve the exercises on the exercises where you are going to graph, identify the domain, the range, horizontal asymptote, base and c of the exponential function. Also in the review you have more exercises. I want you to focus on solving exponential equations. Okay, you have here more exercises to practice. The test review, yes, Mohammed, it is already posted. Okay, I want you to focus on exponential equations. Okay, remember that you have an exercise for 5 point extra, and for the logarithmic function, the only thing I want you to know is that they are the inverse function of exponential functions. Okay, and then on Wednesday we are going to explore more on that and how they relate to each other. Okay, so for the moment, just stop at slide number 25. Okay, make sure that you understand how to work with exponential equations and how to identify all the part of exponential functions. Okay. Any question before I finish our classes today? Yes. Any other questions? Okay, so remember on our classroom we have test number 3 lecture material and reviews and practice. The one that is available, review test number 3 is already available. Okay, class, so thank you for being here. I will see you on Wednesday. Expect from me at least the feedback on the draft, and then we're going to start working with grading your test. So I hope to have before Wednesday. If you have any questions, you know what to do. Send me an email. I will see you on Wednesday, and this class is recorded and going to be posted on YouTube. Thank you, everyone. Have a good day. Good rest of the day. Bye.